Okay, so yeah, thanks, Mark, for inviting. Yeah, as you said, today I'm gonna tell you something about charting globes in asymptotically safe gravity, which is basically a talk based on a work that I did together with Alessia Platania, who is like the group leader here at NBI, and together with a former master student in our group, Jonas Pfeiffer, and Samuele Silveravalle, who's a postdoc at SISSA. And yeah, I might, let's say, know that the title is not yet clear, at least this globes part, but it's part of the talk also to explain it. So let me just start. And if I can change slide. Yes, so this is like the outline of the talk. I want to start giving you the general idea of charting the landscape, what charting the landscape means for me or for us, I would say, in the with quantum gravity. And then I will apply it to Einstein-Weyl gravity. I will give you some motivation. So I will briefly describe like the status of art before our work in Einstein-Weyl, and then I will just go through our results, which let's say intersect asymptotic safety with these works in Einstein-Weyl gravity. But first, let me give you some context, giving you the idea of how can we use quantum gravity to chart the landscape of possible globes. So, first of all, quantum gravity can be many things, because as we know, there are many approaches to quantize gravity. Any of them, I think we all agree that in a certain regime of low energy must be described by an effective field theory, which must take the form of something like this. So I will have like the leading term, which is the Einstein-Hilbert part, plus eventually, if you want, maybe a cosmological constant, if you want to consider it. And then you can have operators containing like the metric, of course, if it's a gravity theory, and matters, which collectively here is encoded in these fields phi. And the shape of this operator O and their couplings Ci, which we will refer to as Wilson coefficient, basically determine the shape of your effective field theory. This, of course, will be valid up to some energy scale, which is fixed by quantum gravity. But yeah, so this is like the generic shape of an effective field theory action. And you see that basically the dependence on the action of the Wilson coefficient will appear also at the level of the field equation, because when you try to minimize the action with respect to the fields, to the dynamical fields that you have also dependence of this Ci. Now, this dependence here on the shape of the effective field theory action from quantum gravity is not completely arbitrary, because the idea of might be able to charting the landscape, so the infrared landscape of effective field theories by quantum gravity is the following. No? So imagine that this is a very nice picture that Jonas did, which is in our paper. Imagine that you have your favorite quantum gravity, which might be string theory, loop, quantum gravity, asymptotic safety, or whatever you like the most. And then this is valid in the very far ultraviolet, because this ideally would complete ultraviolet complete your theory of gravity. And then you try to infer, starting from the assumption of this UV completion, what happens at low energy, lowering the energy and recovering an effective field theory picture of this. So this would select a subset of the possible effective field theories that you would write down. And as a consequence, through writing down the field equation, you would obtain different objects, different spacetimes, which usually extends the ones that are present in general relativity. Here in this talk, I will focus mainly on localized object, on on, let's say, black hole, whether they are black holes, stars, wormholes, but with a pretty generic viewpoint in the sense that I will not specify any feature of them. So I will not focus on just black holes or on just wormholes. And along the paper, with let's say the aim of being generic, we decided to name all the possible, how to say, quote unquote, isolated object that comes down from an equation, a field equation of this kind, as gravitational localized objects. Because okay, actually, because it sounds good, we needed a term and we went for it. Which glob as a word in English, as I understood, googling it, is just a clump of something, which fits best the idea of what I'm gonna talk about. And also, Alessia particularly liked this image that pops out on Google when we Google it, and so we went for it because it's kind of cute. But jokes apart, like by globs, I mean all these kind of solution, landscape of solution, localized solution that can emerge from minimizing the action with respect to the field content. So the idea is the following. So you have a UV completion. This will lead to a particular subset of EFTs, and this will lead to a particular set of globs through the field equation. Now, this is pretty generic, and I want to specialize to the case of Einstein-Weyl gravity. So why Einstein-Weyl gravity? For three different reasons, mainly technical reasons, because it's like the first, the simplest maybe extension that you can have to GR with non-trivial landscape. You just add a single operator to the GR1, to the Einstein-Hilbert one, which is the Weyl-squared here, for which basically you have a non-trivial landscape, because we will see that there are many solutions other than just the usual Schwarzschild black holes that we know. We will see that also a lot of work has been done in the direction of classifying this solution, which serves as a basis for our project, basically. So globs in Einstein-Weyl have already been classified. And also from the FRG side, beta function are known for quadratic gravity. So this is just a subspace of quadratic gravity. And we know that there is a UV fixed point, which in this case we will see has an irrelevant direction, which makes like the computation sensible. All these 3 points we will see later. Just a comment that you introduce a new coupling, so you introduce a new mass or length scale associated to the new coupling. And usually this is associated with the Gauss degree of freedom, presenting quadratic gravity generically, also in Einstein-Weyl. And yeah, this can be a flow. Someone can argue that this can be a flow, but in the spirit of asymptotic safety, we didn't care about it in the sense that we considered it as a result of some truncation artifact. So it's actually something that we do not truly believe is there if you consider, let's say, the whole tower of operators of your effective field theory. But yeah, this is just to mention what I wanted to tell you is like what are the shape of these globes in Einstein-Weyl gravity. Specifically, we will look for spherically symmetric solution. So we will. This is the action that we consider. And in this work by Samuele Silveravalle and Alessandro Zuccotti, they basically solved the equation of motion for spherically symmetric metric and classifying all the possible solution. Working basically, how did they do that? They worked in a weak field limit to look at the shape of the metric far, let's say, in the region where the space-time is almost asymptotically flat. So with f and r basically being 1 plus correction of order of this parameter epsilon, and solving the problem at a linear level in epsilon. If you do so, the field equation solves for f of r and h of r to have this shape here, where you can recognize the first two terms in both functions are the one characterizing the Schwarzschild term. But in addition to that, you have a Yukawa-like term, which is the exponential of minus m2r, where m2 being exactly the mass scale introduced by the new coupling. And associated to that, we have an S2 minus, which is an integration constant of the problem. It's not associated to any conserved charge, as far as we know, to any hair, let me say. So basically, we have the usual ADM mass M, and then as a parameter, S2 minus and M2, okay, as parameterizing your solution from the asymptotic region. And then they did like to determine whether this object can be, let's say, actual black holes or naked singularities or wormholes or something else. Like they said, okay, we have the solution far away from the center, and we can study the asymptotic behavior like in a Frobenius-like expansion with an ansatz like this, where you can see that F and H are parameterized in this way. So they start with a power P around some point R0, and then they have like an expansion of series with integer or non-integer powers, depending on how you select delta. And this allows for you to track the behavior of F and H, both near the singularity, if you put R0 equal to 0, or let's say, in some cases near the horizon, if R0 is different than 0. So basically, all the solution can be classified with the two exponent P and R, and the number delta that you put here, and R0. So that's the technical side. Once you are playing with these four parameters, you can match the solution with the asymptotic behavior of the function like this. So but maybe things are clearer if I go directly to the result of their study, because basically what they got was a diagram which is parameterizing the axis. Basically, we have M, the capital M, S2 minus, and M2. So it's a three-dimensional diagram, morally speaking, where basically you can classify different solution that corresponds to different matching of this F and H function with the ansatz that I told you before. And basically, in function of S2 minus and the ADM mass M, we have, you see, different type of solution. So I want to talk a bit about this diagram, which contains different ingredients. So first of all, we can see that M2 enters the computation, but just quote unquote, just as a scale factor. Basically, M2 changing M2 amounts to rescaling, zooming in or zooming out this diagram, which doesn't modify the shape, but just let's say modify the axis. So fixing M2 to some energy scale would fix the axis here, and we will see that. And second of all, like we see that there are a different solution with respect to GR. Of course, the GR case in the spherically symmetric case is just a Schwarzschild solution, which corresponds to this black dashed line, which is S2 minus equal to 0. So this is the Schwarzschild line, let's say. But then we can have, as you see, like naked singularities, both repulsive and attractive, which are labeled type 1 and type 2. We can have wormholes, which are non-symmetric, because, like, colloquially speaking, they lead to a universe of finite size, if I remember correctly, on the other side of the trough, which is type 3. And in the boundary between type 2 and type 3, we have this colored line, which corresponds to black holes, so object with an horizon, but different from the spatial one. So you see, we have a lot of things to enrich the landscape more than in general relativity. Okay, this diagram cannot be taken. I mean, this is just a plain analysis of the whole possible solution, spherically symmetric and static solution of Einstein-Weyl gravity. What we added with respect to the previous analysis at the classical level was just to notice that this analysis is valid in this regime, where S2 minus is much smaller than M2 to the minus 1. Because if you look at this term of this expansion, basically, since you are expanding around flat space-time, you require that this term, which goes like 1 over r, is the same has the same magnitude of this other term, and this leads to this condition. So basically, you should trust this diagram just in this regime here, so you can depart from the Schwarzschild line by 1 over m2 if you want. And the second thing that I want to mention before going to quantum gravity, let me say, is that this diagram is an analysis of all the possible solutions coming out from the field equation, but for example, not all of the solution would be phenomenologically viable if we look at the object that we observe in the sky. Because, for example, there have been studied like the properties of this object, and if you look for this object to serve as black hole mimickers, you would exclude all these light blue region because these repulsive negative singularities do not, let's say, share the same, let's say, do not cannot play the role of black hole mimickers because do not share the shadow of black holes actually. So you have phenomenological constraint to put on top of it. What I want to explore is the following idea, because, okay, we have the diagram, we have like constraints which comes from the phenomenology. What about putting other constraints, complementing other constraints coming from quantum gravity? And in particular, of course, I will talk about asymptotic safety as the ultraviolet completion or as the quantum gravity theory in this particular case. So this make me come to this point where basically we want to use asymptotic safety to constrain the whole phase diagram. So how do we do that? We take our action, which is like the Einstein-Weyl one, and we stop at this truncation level. So this is the truncation that we will consider. As I told you, basically the beta function for this kind of system has already been studied. Actually, there is this paper here by Benjamin Nor, which is more general because it takes into account the full quadratic gravity case. So we just took let's say the beta function given in this paper, and we reanalyze the flow in the subspace in which the term r² term is put to 0. So we basically just keep the term that interests us. And what we find is that we have a flow that you can see here, which actually possesses an UV fixed point. And as I was anticipating here, this UV fixed point has a relevant and an irrelevant direction, meaning that this point is ultraviolet attractive only along one direction, which here is emphasized to be this thick colored line that you can see in the diagram. Of course, there is another fixed point which corresponds to the Gaussian one, where the dimensionless coupling are small. So exactly, these are the definition of the dimensionless coupling, as you see, label the axis here, and these are the value of the fixed point and the critical exponent. And as you see, we have opposite sign to critical exponents, confirming that there is one relevant and one irrelevant direction. So what does it mean? It means that in principle, we are able to give a prediction on the landscape, which in this case corresponds to a zero-dimensional landscape, meaning that if we assume our, let's say, theory to be ultraviolet complete in the sense of asymptotic safety, basically we assume that along the RG flow, our theory, I mean, yes, our theory will hit the ultraviolet fixed point. Meaning that if you reverse engineer the reasoning, you can start from the ultraviolet fixed point and look at the only direction which stemming from here, hit the Gaussian fixed point. And following this trajectory here, basically one can infer, like can extract the value of the Wilson coefficient in the way I'm going to explain now. The idea is basically the following, because since you're going towards like the IR fixed point along this unique UV complete trajectory, basically the ratio between the dimensionless coupling is in this case equal to the ratio between the dimension full couplings, because the canonical scaling, the canonical mass dimension near the Gaussian fixed point is in both cases proportional to our FRG scale squared, so our proportional to k squared. And as you can see, in terms of the mass scales that we have, this would in principle gives m2 square in Planck units, if you want. So we exactly did this, provided that this prescription work, provided that in the limit for k equal to 0, you know, and you fix like this running Gn to be like the Newton's constant that we know, so 1 over the mass Planck square. This seems quite, let's say, trivial and straightforward to do, but actually, if we go and look closely to what the system does, we discover that we have a problem that we have encountered also in another work, in another asymptotic safety seminar, the one by Francesco Ferrarin, because we encountered a similar problem in that other work, is that, and this is something that is included in a quite generic, as a quite generic feature in effective field theories, is that basically here, when you have when you analyze the RG flow, you're basically integrating out massless fluctuation, and this in the k dependence of the dimensionless coupling arise as a logarithmic, let's say, scaling near the Gaussian fixed point. That means that you see, we have still the canonical scaling, which is k over k0, where k0 is a reference scale squared. But then the dimensionless Weyl-squared coupling have this term here, and as you can see from the picture, we see exactly that. Now this is a log-log picture where we have both g and gc squared depicted, and we fixed k0 to be the mass Planck, and you see that after the k equal to mass Planck, we enter the fixed point regime, and so the couplings tend to a constant. But before, or approaching like smaller and smaller scales, we see that in this log-log plot, we have two lines with different slope, which is exactly taking into account the fact that there is a logarithmic dependence of one of the two coefficients. So the point is that we cannot straightforwardly take the limit of this ratio, because otherwise we have a logarithmic divergence as k approaches 0. This is, of course, not the, let's say, not a novelty, because as I was mentioning before, is an obvious question, but not only like in FRG computation, but is how to treat this kind of logarithms also in EFT is an open question, where they in general arise as logarithmic for factors in the action. But yeah, so what we need is a prescription to single out the finite part of the Wilson coefficient to actually give a prediction. And this prescription has been, let's say, proposed in these papers by Ivano Basile, Alessia Platania, and Benjamin Nora and Alessia Platania some years later, where basically they observe that we can subtract, if you want, by hand the logarithm, singling out the finite part from the Wilson coefficient to define the Wilson coefficient. But in doing this, one have the freedom to choose the scale at which to subtract the logarithm. Basically, you have to identify k0 with something and then plug it into this formula to get a finite value for the IR value, for the infrared value of the Weyl-squared coupling in this case. Now, if we are talking about gravity, there is just a single sensible scale that one can use, and indeed we actually fixed this scale to be the Planckian mass, but This is arbitrary, actually. This is debatable, let me say, when the system have multiple scales. But anyway, in this case, we operated like that, following the prescription that is described in this paper, and we subtracted basically the logarithm by hand, fixing the scale, the quantum gravity scale to be, or the scale determining the fixed point regime to be the mass Planck, and we obtained a finite result operating this limit here. And the finite part that remains identify for you the Wilson coefficient. So basically, we identify the coupling GC2 from which we can extract the value of the mass M2, which in this case turns out to be 1.4 mass Planck approximately. This is nice because this can be plugged in the classical analysis, and we can, let's say, see what is the impact of these results into the phase diagram of Einstein-Weyl. And actually, this is the phase diagram, updated phase diagram with our value of the mass. And as I was telling you, basically fixing them two in the plane of S2 minus and M is fixing basically the scale in the axis. Now we fix the scale in the axis to be Planckian units, basically. And we implemented the two, let's say, observation that I have basically said before to you. So first of all, that S2 minus must be much smaller than 1 over M2, which at this level with this constraint, like M2 being 1.4 Planck mass, means that S2 minus, let's say, is of order of Planck length. And indeed, we actually fixed M2 to be 1.4 M Planck. So the resulting diagram is pretty interesting because you see that basically with this blurring out this region and setting the scale, you find out that the whole landscape of possible solution of Einstein-Weyl gravity reduced drastically, and you basically exclude all the possible type 2 solution, where I will show another couple of plots where this is more clear, especially in the range of large masses. If you have a large ADM mass, basically type 2 solution are not here anymore. And you exclude a big part of non-Schwarzschild black hole, as you can see, like the line has been cut. And in any case, you basically deviate from the GR solution by something which has an S2 minus of order of the Planckian length. So apart from deviation of order Planckian, you basically are within Schwarzschild. And yeah, so this was an implementation of the idea that I was saying before. Let us see a couple of plots more, because basically I have in this case I think like the picture more how to say apparent in some sense, because instead of taking a section of M and S2 minus, here we took a section at constant S2 minus or at constant M, and you exactly see what I was telling you, basically, that if you fix S2 minus to be positive of order of Planck length, you see that basically you exclude all, by quantum gravity, you are excluding all kind of solution but the type 1. Which complemented with the phenomenological observation actually would exclude basically everything, because type 1 are not phenomenologically allowed. If we instead select a negative S2 minus, we have like a different kind of solution, but here as well you see that type 2 solution are highly suppressed. And the same is true if we fix like the masses. Still we fix something at Planckian regime, because like far from Planckian regime we don't see much, and other than Schwarzschild. And you see that basically also here basically we can have other than Schwarzschild just type 1 and type 3 solution. And yes, so yeah, let me comment a bit about this. So what I showed you is basically that quantum gravity can tell us actually something about the um, infrared landscape of the theory. I think a nice viewpoint again is that this should serve not as a I think per se standing alone, but must be complemented with phenomenological constraints, and this is very powerful in charting, let's say, the viable landscape. Of course, in this case, we have considered the case of Einstein-Weyl gravity. So it's a proof of concept, is very simplified, and we do not aim that Einstein-Weyl gravity is a true and good description of, let's say, our reality, but it gives us a glimpse on how things can be done. In particular, this fits, let's say, within the asymptotic safety assumption, because within asymptotic safety, like we have a prescription which has its own arbitrariness, but at least we have a prescription to apply this formalism, this idea, let me say, and to map out part of the low energy landscape, which in particular, in this case, for Einstein-Weyl gravity, this favors attractive naked singularities and non-GR black holes. So basically, if I follow like this complementation with phenomenological constraint, I would say that only wormholes remain viable black hole mimickers for Einstein-Weyl gravity. And yeah, of course, this picture is not at all complete because like one would want to go farther, and yeah, we can go for an outlook which would be like, first of all, there is this issue of having to deal with logarithm, which, to be fair, has not much to do with, I mean, it's not an issue of the FRG computation. It's more an issue of understanding the roles, or the role of these logarithms at the level of the field equation, because we know that anytime you have massless fluctuation, logarithmic form factor arise, and or more generally in an EFT perspective, you can have this logarithm in your effective field theory action. And we would like to, let's say, at some point, understand a way to implement like this logarithmic form factor in the field equation, and to see like how they modify the landscape. Because if you understand that, then you get rid of the arbitrariness I was talking above. So basically, there, let's say, there would be already a prescription to fix the scale and to get rid of the logarithm and understand like the finite value of the Wilson coefficient. And another possible way to go would be like to apply these how to say, this machinery to more sophisticated model. And actually, well, other than Einstein-Weyl, we are working on applying this to the case where the ghost degrees of freedom is not present. So basically, we took the Gorov-Sagnotti term as another operator to add to the action, because we know that Einstein-Hilbert plus Gorov-Sagnotti, basically the Gorov-Sagnotti operator represents an action with only essential operator, so just a theory propagating gravitons, not having any more ghost degrees of freedom. And we are working with, let's say, Jonas, Alessia, and Samuele in this direction. But this, again, would be tantamount to recompute the phase diagram, not much to work on the FRG side, where the results are already known. And yeah, so basically this was it, and I'm happy to take question if you have some, and I would like to thank you for the attention.
All right. Thank you very much, Francesco, for the nice talk.